The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so last time we talked about this IR UV connection between the bulk and the boundary. So the key thing is that let me write down the metric here, the ADS metric in this Poincare coordinate. So this is the boundary is at z equal to 0. And when you increase z, you go to interior. And then for each constant z, you have a Minkowski space-time. You have a Minkowski d. So this is ADS d plus 1. So each slice is a d-dimensional Minkowski space. And due to this redshift factor, the more you go to the interior of the space-time, then corresponding to the lower energy process when viewed from the field theory, when viewed from field theory. So here is the same process happening here compared to happening here, and here corresponding to the IR process, and the boundary corresponding to the UV process. Okay, so this is a key relation between the bulk and the boundary series. And also this gives you an intuitive understanding where does this actual dimension come from the field theory point of view. Then from the field theory perspective, this actual dimension can be considered as a geometrization of the energy scale. Okay? And we know that the physics change with the energy scale from the field theory point of view is called the realization group flow. So how physics evolves when you change the energy or length scale. In the field theory, it's called realization group flow. So you can also view that the evolution in the gravity side, say from the boundary to the interior, and this flow in the z direction can be considered as to geometrize the realization group flow of the field theory. Okay. So any questions regarding this? Good. So now let's talk about some further aspect of the duality. So the duality is that once you realize there's a such relation, since the two sides are completely different objects, so the game is that you really have to do lots of guesswork. So you guess how should this quantity. Yeah, essentially you have two sides if you want to relate things on two sides. And you have to do guesswork. So how does this quantity translate into that quantity, etc. And then check the consistency. Okay? Yeah, just like you don't know two languages. And then you have to guess between the two languages and then build up the dictionary. And we will be doing the same. So we will be doing the same. Good. So now let's do the so this is more like a review of what we already said. So let me be more explicit. We have input for super Yang-Mills theory. We have input super Yang-Mills theory, and then here you have type 2B string. In ADS5 times S5. So let me just write down ADS5 just for simplicity. Yeah, say S5. Okay? So here on this side, there is a conformal symmetry, which we explained before because this is a 4-dimensional theory. So the conformal symmetry of a d-dimensional series SOD, 2. And on this side, there's a precisely the same group, which is isometry of ADS5, which is precisely also SO4, 2, okay, which we reviewed before. And you can write down the transformation on both sides. In your P set, you have checked some of them that they actually one-to-one correspond to each other. For example, this special conformal transformation. And the others, like translation or rotation, etc., it's clear.
So, but in the right-hand side, we still have some like SO5 in S5.
No, I will talk about that.
Okay.
Yeah. And then, so this is more like a space-time symmetry. So this is more like, so this is a space-time symmetry related to the, from field theory point of view, this is a space-time symmetry. So in the for super Yang-Mills series, there's also global symmetry. We discussed before. This is also global symmetry, but this is a global symmetry associated with the space-time. And there's also a global internal symmetry, SO6 internal symmetry. In super Yang-Mills series, we discussed last time, there are 6 scalar fields. You can rotate them each other. And this is, can be considered as coming from the D3 brane. You can rotate the, say, 6 transverse directions. The symmetry in rotating the 6 transverse directions. And on this side, there's exactly the same symmetry. So now this is isometry of S5. Okay? So the isometry of S5 precisely gives you SO6. So you have exactly the same SO6. Okay? And we will not be explicit. You can also actually map the supersymmetry between them. You can also map the supersymmetry between them. So N equal to 4 supersymmetry. So there's a 4 supersymmetry, which just comes from N equal to 4. And because you have conformal symmetry, then the conformal symmetry does not actually commute with this 4 supersymmetry, then generate another 4 supersymmetry. And anyway, so essentially you have 8 supercharge of the wild spinner. And yeah, so this altogether is 32, say, real supercharges. Sometimes we. Okay? So when we say N equal to 4, so this is N equal to 4 in terms of 4-dimensional wild spinner. So your supersymmetry have 4 wild spinner as the supercharge. But the conformal symmetry generate another 4. So altogether you have 8 wild spinner, 4-dimensional wild spinner as the supercharge. And you know that for each wild spinner in 4 dimensions, there are how many components? How many components are there for wild spinner in 4 dimensions? 4. Because it's a 2 component, but each component is complex. And so there are 4 real components. So altogether you have 32 real charges. Okay? And similarly, you find, I will not do this side, you find the same amount of supersymmetry. But in this case, for example, the low energy limit, let's just talk about the low energy limit of this theory. So the low energy limit, as we said before, it just have to be supergravity. So it have to be supergravity, then you find you actually have exactly the same amount of supersymmetry in this geometry. And but the interesting thing is that by definition, supergravity, the supersymmetry on the gravity side is actually local. So you actually have same amount of local supersymmetries. Okay. So if you look at this correspondence between each other, then you actually see a pattern. Okay, so now let me make some remarks. Okay. So if you look at this structure, this mapping here, you see a pattern. On this side, all these symmetries are global symmetries. But on this side, all these symmetries are local symmetries. So this I just said that in supergravity, the supersymmetry is local. And the space-time isometry is just subset of a space-time coordinate transformation. And space-time coordinate transformation are local symmetries. Okay? So the isometry is a subgroup of diffeomorphism. So diffeomorphism just means the coordinate transformations, and these are local symmetries. Okay, and local symmetries. So we find now we actually have a. Now we find the mapping is that the globe on the field theory side, the global symmetries is mapped on the gravity side into the local symmetries. Okay. So for each global symmetry in the field theory side, there's a corresponding local symmetry on the gravity side. Okay, there's a corresponding local symmetry on the gravity side. But you may immediately ask a question. On the gravity side, if you talk about diffeomorphism, then this is a huge group. Certainly much larger than what we are talking about the isometry here. So why we are only talking about the isometry rather than talking about the why we don't talk about the other part of the diffeomorphism, only talk about isometry. So what's special about isometry? So the second remark, why isometry? Why only isometry? Why only isometry? Yeah, why only look at isometry? But let me just save time not to read. Okay? So the isometry is important for the following reason, because even though this is a subgroup, but this is a, so as I mentioned last time, when we talk about the quantum gravity, when we talk about string theory in anti-de Sitter times S5, in terms of ADS5 times S5, you should keep in mind that this ADS5 times S5 refers to the asymptotic geometry. Because as a quantum theory, the theory can fluctuate in the middle. Okay? And the isometry can be considered as a subgroup. But nevertheless, even though the space-time fluctuates, but the ADS5 times S5 specifies the asymptotic geometry of the space-time. Okay, specify the asymptotic geometry of space-time, and the isometry is precisely the subgroup which leaves the asymptotic form of the metric invariant. Okay. So these are not ordinary diffeomorphisms. So the ordinary diffeomorphisms, so ordinary gauge transformations, let me just say it more generally. By gauge transformation, also means the diffeomorphism or just general gauge transformations. So when we talk about the gauge transformations, say for example in QED or in QCD, etc., we always assume, so the class of gauge transformation, we consider we always take them to be fall off sufficiently fast at infinity. At infinity, okay? So we always, when we talk about gauge transformations, say when we talk about typical diffeomorphisms, these are kind of transformations where we assume they go to 1, say at infinity. And these isometries, which leaves us asymptotic over the metric invariant. So these are essentially the large gauge transformations. Because they don't, okay? And so-called large transformations is that they don't go to the identity at infinity, okay? And of course, this is precisely those large gauge transformations which leaves the asymptotic invariant. So in the sense, these large gauge transformations can be considered as the global part of the diffeomorphism, okay? So any questions on this? Yes?
What does it mean that those isometries are local? I mean, when you do isometry in S5, meaning the coordinates in ADS5 can be random? What do you mean when you say that isometries?
Yeah. Yeah, these are just coordinate transformation. Coordinate transformation always defined point by point, right? Yeah. Yeah, just these are specific coordinate transformations.
And what happened to gauge symmetries in N4 Young-Mills?
Sorry?
What happened to gauge transformations in the Young-Mills part?
No, the gauge transformation in the Young-Mills part, you don't see it. Gauge freedom, just redundant freedom, you never see it on the other side.
So does this exhaust all symmetries of the Young-Mills part?
Yeah. It exhausts all global symmetries in the Young-Mills theory part.
Not local.
All the global series on the Young-Mills side, and not local symmetries.
We didn't discuss them yet, but they are there.
There's a UN gauge group there, and but they don't have correspondence in the gravity side. And we know the reason we don't consider the gauge symmetry because they correspond to redundancies, and they don't have to be present on the other side. They only need to the physical degrees of freedom to be identical. And this also is the reason I make this remark here. Even though all these global symmetries, they find the corresponding local symmetries on the gravity side. But precisely due to this remark, those things which really map to the global symmetries in the Young-Mills in the field theory can be considered as a global part of the local symmetries on the gravity side. So even on the gravity side, in some sense, you should think of them as global symmetries, and they're large gauge transformations. Okay. Yeah, because the ordinary gauge transformations just corresponding to redundancies of the redundancy of degrees of freedom, and that should not be reflected on the other side.
What do you mean by large gauge transformation?
The large gauge transformation means the gauge transformation which don't vanish at infinity. Yeah, so the ordinary gauge transformation, yeah, just like in QED, when we talk about in quantum electrodynamics, when we talk about gauge transformation, we talk about gauge transformation. The gauge transformation we consider are all the gauge transformations which go to 0 at infinity. And if you consider those gauge transformations which don't go to 0 at infinity, and that's what we call large gauge transformations. And those large gauge transformations essentially is like the global part of the U1 gauge symmetry. In some sense, can be considered as, yeah.
But that is the gauge symmetry in the gravity side.
Yeah, that's right. Yeah, so this is the part of the gauge symmetry in the gravity side, but it's the part, but the part corresponding to the boundary is the part associated with the infinity. Yeah.
Yes, here in isometry of ADS5, we've shown like in P set, it's point-to-point local symmetry. It's like just a space-time point. But how about this conformum in this Yang-Mills theory? What is this symmetry of the object?
Sorry?
What kind of object does this symmetry correspond to? Because it seems
It's a conformal symmetry.
Conformal symmetry of the component of the field. Or
No. It's a conformal symmetry of the Minkowski space. So on this side, you have isometry of ADS. On the other side, you have conformal symmetry of the Minkowski space. So you're asking what it corresponding to on the field theory side, right? Yeah, so that's mapped to the conformal symmetry of the Minkowski space. Yeah.
So the isometry is actually a large gauge transformations.
Right. So the story actually is more general. So the story is actually works more general. So this is the statement for the incompatible super Yang-Mills theory. So the story is more general. So in the case which you have, say, more general, say, duality between a CFT in D dimension, in Minkowski D, with the ADS gravity, ADS D plus 1 dimensional gravity. In any such duality, then you always have the conformal symmetry, which is SOD, 2 on this here mapped to ADS isometry. ADS D, 2. And any, say, internal gauge symmetry, say if you have some U1 global symmetry here, then this will be mapped into a U1 gauge symmetry. Again, in the sense that this U1 global symmetry can be considered as the global part of this U1 gauge symmetry, the part which does not vanish at infinity. And it's always the case that the global supersymmetry here will corresponding to the local supersymmetry. Here, and exactly also in exactly the sense that even for the local supersymmetric transformation in the gravity side, there's also a part which does not vanish at infinity, and that's the part corresponding to the global supersymmetry on the field series side. Okay? Yes?
What are the fermions in supersymmetry on the ADS side?
Sorry?
In the low energy limit on the ADS part.
Yeah.
What are the fermions in the supersymmetry?
Oh, it's the same thing. What do you mean? What about fermions? There will be some fermions.
That's the fermions?
Hmm?
So there is more than gravitons on ADS side in low energy limit?
Yeah, there are gravitons, and there are also some fermions. There's something called gravitino. There are some other fermions, etc. Yeah.
Is it they who carry the U1 gauge charge?
No. Here is more general. Here is more general. I'm just saying. Yeah. In this case, indeed, those. So this isometry of S5, once you reduce to ADS5, And so that just become again become a gauge symmetry, SO6 gauge symmetry. And some fermions indeed are charged on this SO6 gauge symmetry. Yeah. And here it's just more general. So whatever things, just if you anytime if you have some global symmetry here, should be mapped to some gauge symmetry here. Okay. And we will say this a little bit more a little bit later. Do you have any other questions? Okay, so now let's move to the matching of parameters. Again, this is more like review what we discussed before. And so again, let's first so include super Yang-Mills theory, and then this is type 2b on ADS5 times S5. Okay. So previously we said from the relation of the D brane, so the G Yang-Mills square here is related to the 4 pi GS here string coupling. And also from the D3 brane solution, we find that the G Yang-Mills square, we find, for example, here the curvature. So here the curvature radius R have the following form: 4 pi GS n alpha prime square. So the n is the same n on this side. Okay. So the n is the gauge group n. Yeah, I should say the flux n. Yeah. Anyway. Yeah. Let me add something. So n. So the flux. So the n is the number of D branes on this side, which translate into the flux, and so the flux n, and then here is corresponding to you have SUM. Okay. And so this R, this curvature radius is related to the alpha prime square and the GS in this way. And so on this side, so the dimensionless parameter is given by R squared divided by alpha prime. So if you look at this relation, so if you look at alpha prime 4 to the alpha prime square, then you find this is just related to alpha. Okay? From this relation, 4 pi GS is equal just to G Yang-Mills square, and the n, just n. Okay, so this is the relation between the parameter. Any questions regarding this? Okay, and so on the gravity side, we said these are the two parameters. Okay, and of course you also have this n, but these are the two basic parameters. And we can also, instead of using GS, as we said before, you can also use the Newton constant. So the 10-dimensional Newton constant is length dimension 8. Then the dimensionless parameter will be Gn divided by R to the power 8. And the Gn is related to the GS and alpha prime by this formula. Okay. So now you can just use the relation between the GS, exactly translate this into Yang-Mills coupling. You just can use this relation and then use that to translate this into the parameter in the Yang-Mills series side. Then you find, once you plug all those relations in, how the GS and alpha prime, etc. related in, then you find here, actually G Yang-Mills have disappeared in this relation. What you find is that the Newton constant essentially just related to 1 over n squared. Okay? So up to some parameter, just related to 1 over n squared. So if you expand in G Newton, just like expanding in 1 over n squared. So as we said before, we often do dimensional reduction. Dimensional reduction on S5. Then we get the 5-dimensional Newton constant. So 5-dimensional Newton constant is equal to the 10-dimensional Newton constant, and the difference is volume of S5. Volume of S5. Okay? That's from the, we wrote this down before. And Vs5 is equal to pi cube r to the power fifth. And then from here, you can just work out. So G5 have dimension 3. Then G5 divided by r cube, again, only related to n, given by pi divided by 2n squared. Okay? So these relations are often useful in the future. So now let's look at the various limits of this relation. Various limit of this relation. So let's first look at the classical gravity limit on the gravity side. Okay. So as we discussed at the beginning of this class, by classic, we always use h bar equal to 1. So our h bar is always equal to 1. Okay? But quantum gravity is captured by this parameter h bar times gn. Okay? So even though h bar equal to 1, in the limit when gn goes to 0, then you are in the regime which you can ignore the quantum gravity effect. So that's what we mean by the classical gravity limit. Okay, is that this should go to 0, and then alpha prime should go to 0. Okay, so this means the stringy effect is not important, and this is all in the unit of the r. Okay, and here when I write those relations, I have all set h bar equal to 1. Okay. So when I say the classical gravity limit, which is this limit which h bar equal to 1, but the effect of the Newton constant goes to 0. And the reason I'm emphasizing it is that if you have some matter field in this geometry, then those matter fields should be treated as full quantum. Okay, we just don't treat the gravity as quantum, but those matter fields should be treated as quantum. So the classical gravity limit is the same as QFT, quantum field theory in curved space-time. Okay, so gravity does not fluctuate, so you have rigid curved space-time, but your matter field can fluctuate h bar equal to 1, and so essentially we are dealing with quantum field theory in curved space-time. Okay, so in the type 2b supergravity, there are many such kind of matter fields, and they all should be treated quantum mechanically. It's just that you should consider this small. So let's consider what this means. So Gn small as a dimensionless parameter, this translates into field theory side. If we use this relation, so that means n go to infinity. So this is the Nagian limit of the Yang-Mills theory. Okay, this is the Nagian limit of the Yang-Mills theory, which we. And then alpha prime goes to 0. Okay, from the relation between the alpha prime and here, when alpha prime goes to 0, so this is in the downstairs, then that means this should go to infinity. So this means, so this is what the 'T Hooft coupling we defined before, okay? G square n. So this means the 'T Hooft coupling goes to infinity. So now we see a remarkable relation. Is that, so this is essentially what we expect if you still remember what we did before in the Largian gauge theory, in the Largian gauge theory, in the Largian limit, the fluctuations become very small, etc. So this is consistent that on the gravity side, the fluctuation in the geometry is very small. And now we see that this the decoupling of the stringy effect requires on the field series side the strong coupling. Okay, this is also something roughly we said before. Remember, when we talk about Largian gauge theory, in the Largian gauge theory, you have planar diagram, non-planar diagram, etc. And at each level, say at the planar diagram, you need to sum over infinite number of Feynman diagrams, which are all of planar topology. And if you look at just those Feynman diagrams, of course, you don't see a space-time interpretation. And because they are just Feynman diagrams, you don't see a continuous surface. And I already alluded before that a continuous surface can emerge if that diagram becomes sufficiently complicated. And the way to make that diagram sufficiently complicated is to make it to be at strong coupling. Then the strong coupling, then the diagram with many, many vertices will dominate. And then your most dominant diagrams are those diagrams with not those vertices. And then essentially, you go to continuum limits. And so this relation explicitly realizes that kind of intuition. Okay? Yeah, if you don't remember, go back to your loads regarding the Largian gauge theory. Yeah. So this relation is also remarkable for the following reason. Because this limit on the gravity side is simple, we can just deal with quantum field theory in the curved space-time, which we know how to do. But on this side, it's highly non-trivial, because this is an infinite coupling limit. So this tells you that the strong coupling limit is described by classical gravity. Okay. So that means that we can actually use classical gravity to, in principle, solve problems which are strongly coupled. So there are also, of course, there are corrections beyond this. There are corrections beyond this. So quantum gravity corrections on the gravity on this side, you can say this is a classical gravity limit. You take those parameters to go to 0. But suppose those parameters are not 0, but just small, then you can just expand in those parameters. For example, you can expand in Gn divided by R8. And that expansion essentially gives you a quantum gravity corrections perturbatively. And now this is from this relation, and the expansion of Gn then is translated. So this is expansion in G Newton. So from that relation, we see this is become the expansion 1 over n squared in the field theory side. Okay, yeah, just expansion 1 over n squared. Okay. So on this side, you can also take into account that the alpha prime is non-zero. Then the alpha prime corrections, then the expansion in alpha prime. So from this relation, translate in the expansion in 1 over square root lambda. Okay, 1 over square root lambda. So in principle, the corrections in this beyond this limit can again be studied on the gravity side, and then and then the 1 over square root lambda corrections and corresponding to the stringy corrections, and the 1 over n square corrections corresponding to the quantum gravity corrections. Okay? And so this is a classical limit. You can also consider a classical string limit. We considered before. We discussed before. In the classical string limit, then still you consider n go to infinity, which corresponding to Gn R8 goes to 0. But here, the alpha prime can be arbitrary. And here is the to Hooft coupling can be arbitrary. So it can be finite. Yeah, so let me just say alpha prime finite, no longer 0. And then this just corresponding to lambda finite, which is no longer infinite. Okay? So this is just a standard to Hooft limit. So this is just standard to Hooft limit, which you take n go to infinity, but keep lambda to be finite. Okay? Standard to Hooft limit, which we talked about before in the Largian gauge theory. And then again, the corrections in Gn will be corrections in 1 over n squared. So any questions? Yes?
Doesn't small alpha over r squared means large GS?
No, that have nothing to do with GS. This is these are two independent parameters. These are two independent parameters. Yeah.
The expression parentheses, so
Sorry?
there is also n. Okay. Okay.
Yeah, this is the yeah.
Sorry. So in the classical string limit, it means that since lambda is finite, so this means G Young-Mills is 0.
Sorry?
I mean, lambda is finite here,
Yeah.
so G Young-Mills is 0, and it means weak coupling.
No, that's what we discussed before in the Largian gauge theory. The effective coupling is lambda. Lambda is your effective coupling in the Largian limit.
When you draw the diagram,
Yeah. So the lambda is your coupling. Yeah. So the G Young-Mills, G Young-Mills indeed in the to Hooft limit, the G Young-Mills will go to 0 when n goes to infinity, but G Young-Mills is not the right parameter to look at things. Any other questions? Okay, good. So now we can move on further. We can talk about the matching of the spectrum. On two sides. Okay. So from now on, I will just restrict the essentially the semi-classical. Here I should call semi-classical gravity limit, because we still treat the matter fields essentially as quantum, so we call it semi-classical gravity limit. So from now on, so we will mostly just consider the semi-classical gravity regime in the gravity side, because essentially we know very little about the string theory in this geometry. And also I will often use the phrase which apply to the general correspondence and not necessarily just n equal to 4 super Young-Mills theory and the type 2B string theory. And I just use the language assuming there's a general correspondence between some conformal field theory and some ADS gravity theory. Okay? So now let's. So if the two theory have to be the same, two sides have to be the same, then you should be able to map their spectrum. Okay, so you should be able to map their Hilbert space, for example. So, so again, let me just now use the general use the language of the state boundary and the Bach, the boundary of Bach theory. Okay. Yeah, let me go a little bit further. So the boundary theory is a conformal theory with this symmetry. Okay. So for the moment I don't have a symmetry. So that means that your Hilbert space should be organized as the representations of the conformal group, say of this SO D2. Okay. And similarly here, because here the SOD comma 2 is the isometry group and which lives infinity invariant. And again, you should be able to organize your Hilbert space using the representations of the SOD comma 2. And those representations, of course, should be the same. Okay. So say if there's one representation here, then there must be a representation here, and if there's two representations, two some representation here, there will be two identical representations here. Okay. The representation they must match. And on the boundary side, the operators they should also local operators they also should transform the other representations of the conformal symmetry, and again then say conformal local operators should also be mapped to say the field on the gravity. So in the gravity side. And the field which also transform under the field should also transform under this isometry, this SOD comma 2 isometry. Then that should means there should be a one-to-one correspondence between the local operators here and the Bach fields in the gravity side. Okay, there should be one-to-one correspondence on that side. For example, in the boundary, if there's some scalar operator, there must be a corresponding scalar field on the gravity side. Okay. Similarly, if there is some vector operator in the boundary theory, there must be a corresponding the Bach field, Bach vector field on the in the gravity side. And similarly, if you have some symmetric tensor, then this must also be related to some symmetric tensor. Okay? So now I will often use the notation that I use mu refers to the boundary indices, and the capital M, capital N refers to the Bach indices, because they run different dimensions. So then they're not quite the same. Okay. Yeah, 1 second. Yeah, let me just finish. So here I'm just talking about the conformal symmetries, and if the theory have some other symmetries, say some global symmetries or supersymmetries, then again all those fields and the state they should transform on the representations of those symmetries, and again they should all match together. Okay, they should all match together. Yes.
So will we prove that the super Yamil's series really lived on the boundary of the ADS?
No, we did not prove that. No, this is just a postulate.
Oh, okay.
Yeah, this is just a postulate. First, let me just repeat again. Yamil theory lives on Minkowski space. And it's just an observation that Minkowski space is the boundary of ADS. Yes. And then you say, we can imagine that this is the boundary. This relation is related to the bulk and the boundary. Okay. And this is a postulate based on that fact. Yeah. Yes?
One of the motivations for thinking about the holographic duality was to try to escape Weinberg-Whitson theorem. Okay, and all of a sudden it strikes me like, so we're trying to get on the boundary spin to massless particles, but then they will also exist in the bulk.
Sorry?
So.
No, in the field theory side, there's no massless spin 2 particles. They map to some field in the gravity side in the 5 dimensions. So this is some 4-dimensional operator. Then this maps to some 5-dimensional fields.
I need to think about my question better.
Okay. Good. Yes.
So one question. So if it's a postulate that, okay, so I mean it's not required that the theory live on the boundary. So
yeah.
It seems that that's just sort of a convenient way of thinking about it.
Yeah.
But what implications would it have if it actually lived on the boundary? Would it change anything?
Oh yeah, that's what I said before. So this discussion does not depend on that.
Right.
This discussion does not depend on that. You can say I don't need to worry about that, whether this is on the boundary or bulk, etc. These are just some different theories. I want them to be the same.
Right. Okay.
But as I said last time, if you believe this bulk and the boundary relation, then this is powerful, because then you can immediately deduce that the Yang-Mills theory on the S3 times time then is related to the gravity theory in the global ADS, and that's just a non-trivial prediction from thinking the boundary and the bulk relation.
I see.
Yeah, now you can generalize it.
Got it.
Yeah. Yeah, because if I just look at this relation, I have no reason to suspect why. Yeah, you can argue from the symmetry point of view also, but that language is more direct.
Okay.
Yeah. In principle, after establishing the relation between the Yang-Mills theory in Minkowski space-time and this gravity in the Poincare patch, I may also, just based on the group theory aspect, to say that should generalize to the Yang-Mills theory on the S sphere and the global ADS. You may also be able to do it that way. But thinking from the holographic point of view, give you a direct way to argue that. Yeah, give you an alternative way to argue that. Yeah. Yes. Yeah. Also, in your P set, you have checked this holographic bound, and so that's a confirmation of this. Yeah. Okay. Yes.
So what does the massless spectrum field on the right map to if it's the same representation of SOD2?
Sorry, say it again.
So in the representation line, so if you have the massless spin-2 field on the right, what does it map to on the left?
Yeah, we were going to talk about it. We are going to talk about it.
Oh, yeah, right.
Okay, so yeah, so if there are other symmetries, then everything should match. Okay. So now, as an immediate check, you can now just open your old papers, and if you load them, and because in the 80s people have worked out the supergravity spectrum precisely on this space, okay? So even though this relation was discovered in the 1997, but actually in the 80s people already worked a lot to consider this type 2B supergravity on this space. Because this is a maximally supersymmetric space, etc. Anyway, so people have already spent lots of trouble actually work out those spectrum. And now you can just open their paper, then there's a big table about the different fields and their representations, etc. And then you can map them, and then you can immediately see they actually map to certain representations to certain operators, certain representation of operators in the Engels-Ford super Yang-Mills theory. Then you can immediately check them. Okay. and you can immediately check them, just based on the group theory. Just based on group theory, check them. But so I won't go to those details. But let me just mention the most important such kind of mapping for the for these two series, and actually does have consequences for the general story. So the most important mapping. So as we said, on the string theory side, you always have this dilaton. Say this is some scalar field, and this dilaton will appear in the scalar field in ADS5, say for example. And turns out this dilaton field is mapped to the Lagrangian of the equidifferent super-Yang-Mills theory. Okay, so the Lagrangian of the equidifferent super-Yang-Mills theory. So the Lagrangian is a Lagrangian of the equidifferent super-Yang-Mills theory. Say trace f squared plus phi squared, etc. So that's a local operator, and it turns out that operator is mapped to this dilaton. And on the equidifferent super-Yang-Mills theory side, we have this SO6 gauge symmetry. Did I just erase them? Yeah, we have this SO6 gauge symmetry. Then we have the current, conserved current, SO6 conserved current. And turns out this on the gravity side just mapped to SO6 gauge field.
Sorry,
okay.
you said it was an SO6 gauge symmetry on S3?
No, in the equidifferent, this is a global symmetry. But on this side, so this appears as an isometry on the S5. But when you dimensionally reduce on S5, then in ADS5, then there will be a P gauge field which corresponding to each symmetry generators of S5, and that then naturally then mapped to the this conserved current on the field theory side. Okay. And then another universal operator on the field theory side is the stress tensor. So no matter what theory you consider, you have stress tensor. And this is mapped to, turns out, to the metric perturbations. To the metric perturbations. So deviation from the ADS metric. Okay. Again, so at the representation level, this is very lateral. Yes, so this is a symmetric tensor. This is a symmetric tensor. And but physically, this is also lateral. Physically, also lateral. I will elaborate this a little bit further from a different perspective. In a few minutes. Okay. So, do you have any questions regarding this? So now, given this mapping, any operator is dual to a Bach field, then you can ask some immediate questions. Okay, you can ask some immediate questions. For example, the quantum numbers of these operators will map to the quantum numbers of the Bach field, and that's something I said. You can check them their symmetries. For example, not only the representations on the S of under this conformal symmetry should map under that representations, and also the representation under that SO6 will also match, etc. Okay. And so for local operator on the field theory side, yeah. So once we have this mapping, we can immediately ask questions related to operators on this side, and try to ask what's the counterpart on the other side, and ask the field, ask the story about the field on the gravity side, and ask what's happened on this side. Okay, we can then start developing the relations. So now let's start discussing them. So the first thing you can do, so immediate question you can ask, is that given an operator say operator O on in the field theory, okay? So there are some natural questions one can raise about this operator. For example, what is correlation functions, etc. And that we will discuss a little bit later. But now let me discuss a lot of natural questions. And the natural thing to do is to deform your original theory by adding this operator to the Lagrangian. So this is some, okay. So I have an operator. I can put the source, I can put the coefficient, and these coefficients, say, may depend or not depend on the spatial space-time coordinates. And I can always add such a term to Lagrangian. And then this deform my theory away from the original theory. So this is a natural thing to do. And this phi 0 is often called the source. So this phi 0 is called the source. Okay? So immediate question you can ask, and when phi 0 is equal to constant, when it's phi 0 equal to constant, then this corresponding to a change in the coupling. For this operator. Okay. Say if your Lagrangian previously already included this operator, and then if you add such a term, say with phi 0 equal to constant, then you are just changing the coupling for that operator. And if this operator is not there, then you just add a new coupling. Okay. But in general, you can make it space-time dependent. And yeah. Okay.
Why is it coupling since there is no other operators coupling with O? If we say phi 0 is a constant.
Sorry?
If phi 0 is a constant.
No, O is an operator. It's a local operator.
Yes, but there is no other operators. This operator O coupling with.
No. What is the meaning of operator? The meaning of operator is that O is a sum of the product of fields.
Oh, okay.
And so there's already say that this O might be phi cube or maybe phi 4, etc.
Okay. Okay.
Okay. Yeah. So example. So example is O. Say in the scalar field theory, if the field theory have a scalar, yeah. If a scalar field theory have a gauge field, then I can say write O as trace F square, and then this corresponding to change the coupling for trace F square. Okay. So immediate question is, what does this operation? So in the field theory point of view, you can always do this operation. Okay. So the immediate question, what does this corresponding to in the block? Okay. What does this operation correspond to? In the block. Okay. So now I try to answer this question. As I said before, in establishing such dictionary, you often have to do lots of guesswork, and then you check. And the guesswork is based on some very small clues. So people who are able to make good guesses is that they are able to grasp important clues, sometimes from very simple facts. Okay, from very simple facts. And so that is what good physicists do. Is that they can see non-ordinary things from the ordinary things. So, so here, I will try to deduce the answer to this question by starting from this relation. Okay? So, so let me start with that relation. So related to the GS. Okay? So let's forget about P for pi. And now we talked about before, GS, string coupling, can be considered as the expectation value of the dilettante field. So let me actually call it capital phi. So we mentioned before when we talk about string theory that this string coupling can be considered as the expectation value of the dilettante field. And what's, of course, in general, again, the dilettante can be fluctuate, etc. So what normally we mean, say normally in flat space, when we say the dilettante has expectation value, what we normally say is that the value of the dilettante at the infinity, okay? Because the boundary value at infinity, that's how you fix the, yeah. And similarly, for space-time like ADS with a boundary, and the expectation value of this dilettante can be identified with the value of the dilettante at the boundary of ADS. Okay, so here write partial ADS means the boundary of ADS. Okay. So this is the value of ADS, value of phi at the boundary. Okay, so expectation value essentially can be associated with the boundary value of the field. Okay.
You mean if it is a constant? If the expectation value of the phi is constant, or if it's function-wise equal to the boundary value?
No. Think about the following thing. As I said, phi in principle can fluctuate, and its expectation may also be able to fluctuate in the space-time. But the only sensible way to talk about expectation value is to talk about its value at the boundary, because we assume the boundary conditions don't fluctuate. Okay. Yeah, it's the same thing for flat space, and we always specify the boundary condition at the spatial infinity, for example. And in the ADS, which is also space-time with a boundary, then we can associate this the constant parts of the expectation value as the value at the boundary. Okay. Now you have to use a little bit stretch of imagination. The following fact you don't need to. So now we have with this relation we have established a connection between the Yang-Mills theory coupling with the value of phi at the boundary of ADS. Okay. So the boundary value of ADS. Okay. And now remember this Yang-Mills coupling, say up to, yes, I will not be careful about the 1 over Yang-Mills square, or just, this is related, this is the coupling or source for the Lagrangian of n equal to 4 super Yang-Mills theory. Okay. So now we can deduce here two things. In particular, if we deform the Lagrangian, say change this coupling, okay? Deform the boundary by changing the coupling, which corresponding to you add some delta G, say the Lagrangian of n equal to 4 super Young Mills. Okay? Deform the boundary say by changing the coupling. And this corresponding to you essentially change the value, change the boundary value of dilaton. Okay? Because these are related. So now, this example gives us the answer to this question. This example gives us this question. From here, we can deduce first that the dilaton, say, must be the operator corresponding to the dilaton must be the n equal to 4 super Young Mills Lagrangian, as you can already deduce from some other methods, say using group theory, etc. And the second is that phi 0 O in the boundary theory, adding a phi 0 O in the boundary theory must be related. So now I'm generalizing this story. That the Bach field phi, so now I'm no longer not necessarily using the dilaton. The Bach field phi dual to O has a boundary value. Phi 0. Okay? Any questions about this? Yes?
The choice of operator O should be consistent with those symmetries, right?
Hmm?
You're not pre-choosing O.
No, O can be anything.
Consistent with original symmetries of the...
No, it doesn't have to. You can deform the theory without be considered. Yeah, you can break the symmetry. A deformation can break the symmetry. And if you want to preserve the symmetry of the original Lagrangian, then you can choose a certain O, but in principle you can add any O. You can break the symmetry if you want.
Do you have to always then break some symmetry on the ADS part?
Yeah. When you impose this kind of boundary conditions, then you may break ADS symmetry too. Okay? So now we have answered this question. And then, of course, this just provides the answer, then you will check it. And we will check it later using other methods. Now I'm saying it because I already know it's true. But in real life, what you will do, from this example, you will say, this must be the case. Then you start trying to find examples to check it. Okay? You start to find other ways to check it. And we will describe it later. So in the end, what we will describe is a self-consistent story. I will not contradict myself in my later discussion. So if we assume this, I can also use this to argue use this identification. Okay, use this identification to argue these two. So let me call this star and star. Can use this identification to make star and star natural for any duality. Not only say n for super Young Mills and this type 2B gravity. Is that any conserved current in the boundary theory must be dual to some gauge field. In the gravity side, And the stress tensor should always be dual to the metric. Okay? So now I'm going to use this argument to make that a little bit more natural. Okay? So first, so let's first consider this. So suppose I have a conserved current J. I have a J mu. Say for simplicity, let me just take it to be U1. Then I can deform the boundary theory by adding a source for this J mu. So by adding the boundary Lagrangian a term like this, and A mu is a source. Okay? A mu is a source. And then according to this identification, then A mu must be A mu, we should be able to identify it as the boundary value of some Bach field A mu evaluated at z equal to 0. Okay? So this is a Bach vector field. So yeah, Bach vector field. So if this is true, there must exist a vector field dual to this a vector field, and this must correspond to the boundary value of that. But now we can argue why this should be a gauge field. Okay? So now I want to argue this is a gauge field. And to see this is very easy because since J mu is conserved, and then this coupling, so let me call it star, star, star. So let me call it star, star, star. So since this is conserved, and this star, star, star is invariant under the following transformation, A mu goes to A mu plus partial mu lambda x for any lambda x. Okay? So that means that the boundary, so that means the A mu, this A is the boundary value of A. So that means this capital A, that means the dynamics of the dynamics of this A mu should also be invariant. Okay, if I change the boundary value of A by this transformation, the dynamics of A mu should also not change. Let me call it AM. So the Bach in general have a different, will be different. But this is like a gauge transformation. So this is like gauge transformation. So we deduce that somehow this must be some subset of the Bach gauge transformation. Okay. So this, yeah. So now call it star to the power 4. then star to the power 4 must be also must be a subset of some Bach gauge transformation. Okay? So this does not prove it, but make it more natural. This argument make it more natural. The fact that the boundary value of A have such kind of gauge symmetry. So there must be, in some sense, this must generalize some gauge symmetry in the full gravity side. So similarly, you can do this for the metric, for the stress tensor. Similarly, you can do this for the stress tensor. So for the stress tensor, so for the star star, we can add, again, we can add h mu mu x t mu mu to the boundary Lagrangian. And this is the source to the stress tensor. Okay, to the stress tensor. And now, from your knowledge of quantum field theory, when I add such a term to the field theory, it's the same. So this is equivalent to I deform the boundary metric, boundary spacetime metric from just eta mu mu to eta mu mu plus h mu mu. Okay? So let me call this quantity g mu mu b. Okay? So adding such a term, source for the stress tensor, is like you deform your space-time geometry a little bit by this source. Okay, at least when h is very small. Yeah, when we consider the information, we always consider the source is small. Okay? But now, we can argue this thing must correspond to the boundary value of the metric in the gravity side, okay, for the following reason. So if you look at this expression, so if you look at even the pure ADS metric before you do any deformation, so this is just due to the just due to the original theory. So from the ADS metric, so the original ADS metric, the g mu mu component, okay, g mu mu. So let me write this ADS metric in the form, say r square, z square, separate the z square, and with the rest. Okay, so this is essentially the component of the Bach metric along the boundary direction. The boundary value of this metric component evaluated at z equal to 0 is equal to r squared divided by z squared eta mu mu. Okay, so that just comes from the ADS metric. Okay, I'm just this g mu mu, and when you go to the boundary, just given by this. Okay, and this is eta mu mu we recognize just as the boundary metric. Okay. So expect, so this corresponding to deform, since adding this term corresponding to deform the boundary metric, so we expect when we add this term, so this corresponding to deform the g mu mu, now to the 0 become, so we expect this become equal to g mu mu b. Okay? G mu mu b. Okay? So this tells you that the stress tensor must be dual to the metric perturbations in the gravity side. Okay? The stress tensor must be corresponding to the metric perturbation in the gravity side because it's corresponding to perturb the boundary conditions of the Bach metric, corresponding to the perturb the boundary condition for the Bach metric. So this is a very general statement. This is a very general statement valid for any correspondence between the gravity and the field theory. And that also tells you that if you have a theory which is due to a higher dimensional theory, and then that theory, if the field theory have a stress tensor, then this gravity theory must have gravity. This Bach theory must have gravity because this Bach theory must have a dynamical metric. Okay, must have to have a dynamical metric, and if you have a dynamical metric, then you have gravity. So you can say if any field theory is due to a theory of one higher dimension, that theory of one higher dimension must involve gravity. Okay, must involve quantum gravity. Okay. Yeah, let's stop here.